Welcome back to ECE 320A. You don't have to go to the review session if you don't want. I'll try to record that, and hopefully it will get recorded. Exam 1. Wow, is that a week from today? Your first exam is a week from today. There is a process description. You're going to get one crib sheet, front and back, 8.5 by 11. You can bring graphing calculators, no cell phones, no computers. I think the obvious restrictions, no textbook, no notes, but you do have that one page of notes. Homework 2 is due on the next day that we meet, not necessarily right when we meet, but I think it's due at 4 o'clock that afternoon. I have tried to post exam number 1 review material on D2L. Is that, anybody seen that? Yes, so it is there. I always kind of second guess whether it's there or not. There should be several exams, previous exams, that you can look at to try to get a feel for what exam number 1 might look like. Today what I want to do is again pretty full, but I'm going to scroll through some of this quickly, and hopefully you have some in your notes, or you can sort of supplement your notes later. But I want to recap this relationship between the phase voltage and the line voltage for a Y-connected load. The same kind of analysis can be done at the source side in terms of converting from phase variables to line voltages or line variables. Then I'm simply going to state, or I've written down, the definitions or some pseudo definitions of what I consider to be a way to keep track of the difference between these types of variables, phase and line. In some configurations they're the same. Your phase voltage is the same as your line voltage in a delta configured load. In a delta configured load, you have to worry about your line current and your phase current. Those are different. And that's what I hope that you go away with today. We will also introduce different power formulas. We might have a power formula that's in terms of the per phase variables or phase variables. We'll look at the total power, and that one you can write in terms of line quantities, line voltage, line current, and then the phase angle of your impedance at the load. Then if we have time, we'll look at what's really discussed in section 9.6, which is impedance transformations. In a real quick nutshell, if you have balanced, then you can quickly use a factor of 3 to convert between deltas and Y-shaped load or Y-connected loads. So this factor of 3 translates those for you rather quickly when you have a balanced configuration or balanced loads. And if you sort of think of that's kind of small, but the Y is inside the delta. The Y is the smaller quantity. If you now have a delta configured load and you want to convert that into a Y configuration, you can divide all of those by 3 and get the impedances in the Y configuration, or vice versa. If you wanted to find the delta connected load, then you could scale up by a factor of 3. And we may not get there, and that's why I'm giving you that information. If you have unbalanced impedances, you can't use that simple formula of 3. You have to use all of the different values, and that's what we'll go through if we have time, but that's in section 9.6 of your textbook. So that's 220 material. You're already experts on 220. That's the assumption. Here's where we left off last time. We had a Y-connected load, and we want to relate the phase voltages, all these voltages, from a terminal, A, B, or C, to the neutral location in that Y-connected load, capital N. In this example that we worked through, we assumed we have a positive phase sequence, an ABC sequence. So if we were walking around, and that's indicated here, if you sort of get lost or if it seems to be confusing, just start sketching some diagrams or little figures. Here is an ABC phase sequence in terms of a balanced phase sequence. That's A, B, C if you were walking around in a clockwise manner. If it's spinning counterclockwise, and if you're sitting here and watching which phase you're seeing as it spins by, you see A, B, and C. So you can think of it two different ways, or those two ways they should be consistent. With an ABC sequence, we've assumed then a phase voltage magnitude of V sub phi, and the B phase is behind the A phase by 120. The C phase is behind the B phase by 120 also. We can then talk about different voltages. We could get a multimeter and measure between A and N. That would be the phase voltage, V sub AN, or we could measure the line voltage between terminal A and terminal B, and that's going to be different. I hope it's clear, and we derived that last time. Last time we started with KVL, let's say around that top mesh with the air gap voltage VAB. We go into the negative terminal of voltage AB, we come down through VAN, and then we enter the negative terminal of V sub BN. We solve that for V sub AB, substitute in the assumed structure for the phase voltages, the A phase and the B phase, with the magnitudes being equal. All we really have to do is remind ourselves how to go from polar to rectangular, which is cosine x plus j sine x. In this case, it's cosine theta plus j sine theta. If we do that, which we quickly ran through last time, we can combine these real parts and imaginary pieces into 1.5 for the real part, and the imaginary part is the square root of 3 over 2, which if you find the magnitude of that number, 15 squared is 225, so this represents 2 1/4, or 9 quarters if you're thinking change in your pocket, and this is now 3 quarters. So 2 1/4 and 3 quarters makes 3. That's where this square root of 3 is coming from in terms of this scaling difference between the line voltage magnitude and the phase voltage magnitude. Again, this is in the Y configuration, and the phase voltage started out at 0 degrees, and consequently your line voltage is 30 degrees beyond or ahead of the phase voltage in this conversion with the ABC. And you could then look at this Phasor diagram. Last time I think I simply drew the first two arrows, V sub AN and V sub AB. But you can fill all of those in. All of your red lines should be 120 degrees apart or away from each other. It's balanced. All of your blue lines are 120 degrees apart. It's a balanced set of voltages. It's just that now you have to, or you can remember square root of 3 at 30 degrees for an ABC sequence, for a positive phase sequence. And if somebody now gave you the B phase voltage and asked you for the line voltage VAB, you should be able to find that. Meaning if somebody gave you V sub BN, you could find V sub BC by advancing by 30 degrees and scaling by a square root of 3, and then realize for a positive phase sequence that is 120 degrees behind the AB line voltage. Meaning keeping track of this diagram is helpful in understanding the relationship between phase voltage and line voltage. And you may not have V sub AN right at 0, but you can rotate this entire shape or phasor diagram and locate the angle that V sub AN is located at. If it's at 10 degrees, then everything gets rotated counterclockwise 10 degrees in this diagram. Questions on this diagram? Meaning, if somebody gives you a line voltage, you can compute the phase voltage if that would help you with your calculations. Or vice versa. If somebody gives you a phase voltage and you really need to know the line voltage, you can find that from knowledge of this relationship between phase voltage and line voltage in the ABC or positive phase sequence configuration. If you looked at the ACB sequence, the circuit is the same. It's still Y connected. Your KVL equation is still the same. It's just now you use what for your phasor values for the different phase voltages. What's the angle on V sub BN? Really all you have to do is go back to the defining 3 letters that are consistent or the same as negative phase sequence, your ACB, and now you know that if you were walking around that phasor diagram in a clockwise fashion, you would start at A, you would then run into the C phasor after 120 degrees, and so this is now at 120 degrees minus. You keep walking clockwise and you will then run into the B phase. That's the ACB or the negative phase sequence. That's minus 240, which is equivalent to plus 120. And if you plug those values into the formula that we used before that we obtained from the KVL, you will find that now if you needed to convert between phase voltage and line voltage for a negative phase sequence, for an ACB, you still scale the magnitude by this square root of 3, but now it is behind the particular phase voltage by 30 degrees. And all of this, if you don't remember anything, just look in your book and write down figure 11.9, and that should sketch these 2 different relationships for the positive phase sequence and the negative phase sequence relative to which one is leading, which one is behind, etc., the different phase voltages. Questions on this? I'm going through this quickly because I don't want to spend a lot of time on it, but here are the definitions. In words, the phase voltage, then you look at the impedance in a particular phase. If they say, oh, what's the phase voltage at the B, in the B phase? You would find the B impedance at the load and try to find what is its voltage across that impedance. That would be the phase voltage. That may or may not be the same as the line voltage, depending on how that load is configured or interconnected. The line voltage is just between two lines. So the line voltage, you could really expand that out and say line to line voltage, where 2 is TO. You have TWO lines or TWO terminals that you're dealing with, and that's your line voltage. Again, that may or may not be the same as your phase voltage depending on your configuration. When do these voltages differ? Under what configuration? And this is a 50-50 proposition, isn't it? You only have two configurations to deal with, delta and Y. So the Y configuration is where you have to distinguish between your two types of voltages. Phase voltage and line voltage are not the same in a Y-connected load. Likewise for a Y-connected source. Your source phase voltage is not the same as your line voltage at the source terminals. Likewise, we can define, or I've tried to quickly define, the phase current and the line current. The phase current, you identify either the source or the impedance that you're interested in, and what's the current that's flowing through that. That's your phase current. The line current here is the current in your transmission line between your source and your load. So the line current is the current flowing through a particular transmission line, and that can be the same as your phase current. In what configuration? When is the line current the same as your phase current? Flip a coin, huh? We were doing quarters before. Do you still have that quarter? We had 9 quarters, and then we added 3, ending up with 12 quarters to give us a 3. That was the square root of 3. Now just draw your diagram and say, okay, when is the current, the line current, going to be the same as the current going through an individual impedance? Pardon? Why? Is that a question? WHY or WYE? It's the Y configuration, isn't it? The WYE. The line current and the phase current are the same in the Y configuration. That has different interpretations, just like 2, right? TO, TWO, or TOO. And we will use them all today. Questions on those definitions? You need to make sure that it's clear, because it's very critical that when you're computing power per phase, what are you using? What quantities are you using? Which voltages and currents do you use? Phase. You always use the phase. Well, when they're equal to the line, then you can use the line. But it's the phase currents that you're interested in. All right, here's a quiz. There's our Y-connected load. And I need you to fill in the blanks. Here is this is at the load side, and I've labeled V sub AN and V sub AB with the appropriate polarities indicated. In this Y-connected or configured load, V sub AN is fill in the blank. Voltage. And you only have 2 words. We just talked about phase and line. So those are the 2 that you have to pick from. Again, you could pull out your quarter and do a coin toss if you needed to, but I hope by a week from today you don't do a coin toss. You're confident in what you want to write down. Capital V sub capital AN is what voltage in this diagram? Anybody else want to venture an answer? I won't say a guess. What is it? Have you already filled in your blank? You're confident, you're taking notes in pen, you can write it down. What did you say? Phase voltage. Is that correct? And now, just for convention, let's just say that we call that magnitude of V sub AN. That phasor will have an angle, but a lot of times it's nice to just deal with the magnitude of the voltage. And if that's the case, if it's a phase voltage, we usually subscript that V sub phi. And we'll relate that then to, now, V sub AB. Hopefully, your knowledge of circuits allows you to realize that V sub AB is not quite the same as V sub AN, so they can't really be the same word that's amplifying voltage. So this one is the line, isn't it? Now, how is the magnitude of V sub AB related to V sub phi? Root 3, right? So this is now the square root of 3 V sub phi. Or we might actually just call this V sub L, or the line voltage. Somebody may just go out into the field and measure the magnitude of the line voltage and say, I measured the line voltage and it was 238 volts. And you go, oh boy. Do we have to send him back out into the field to take some more measurements? Maybe, maybe not. Let's see what we can derive with respect to our formulas. I sub AA. I almost slid it completely off. What does it represent in this configuration? Phase or line current? Now you can have a two-headed coin, can't you? It's both, isn't it? It's either. It's the same in this configuration because the current is the same going in through the transmission line and also through individual phases or impedances. Now, with that information, can you give me a formula for the real power? And now what can you do if you kind of are forgetting things? You could always draw your triangle, draw a picture, right? And you should have an angle in that picture. You have a horizontal line and a vertical line. With the real power, which one are we interested in? Horizontal, vertical, or hypotenuse? The horizontal. But let's write that in terms of phase magnitudes for voltage and current. What would this be? V sub phi, that's just a number, that's a magnitude. What's the apparent power? If I said, what's the apparent power, how would you compute the apparent power? VRMS, IRMS, they're magnitudes, right? But that's the length of the hypotenuse, isn't it? VI, that's not the horizontal line. How do I get horizontal from a hypotenuse if I have an angle? Cosine. So now I have to multiply that by the cosine of theta sub phi, where theta sub phi is the impedance of your impedance, which if you knew the angles of your voltage and current, you could say that this is now theta sub v sub phi minus theta sub I sub phi. That's the difference between your phase voltage angle, or your voltage's phase angle, and your current, your phase current angle. Is that okay? Now, that buddy of yours just went out and measured the line voltage, didn't he? And maybe he gave you the line current. Can you use either of those two directly in this formula? For the Y configuration, which is which? Or which one can you use? The line current. That's the same as the phase current, isn't it? So you know I sub phi. But from your knowledge now of how to convert between phase and line, it's now this square root of 3 difference, isn't it? So we could solve that V sub phi, or square root of 3 V sub phi equal to V sub L equation for V sub phi, and rewrite that formula in terms of our line voltage magnitude. Meaning we can now say that the power per phase is now this V sub line over the square root of 3 I sub line, since that's the same as I sub phi, cosine of the impedance of your, or the cosine of your angle of your impedance. So now all anybody has to do is give you the magnitude of your voltage, line voltage, the magnitude of your line current, and tell you, what's that? Another way of writing that. PF, isn't it? Power factor. So if somebody gives you the power factor of your load, you've got it all available to you, don't you? Or they could give you the impedance, and then you could find the angle of that impedance and take the cosine of that. There's a lot of different ways of solving or plugging in numbers to generate the per phase real power. That's power in one phase. What's the total power, real power? That's what I'll call P sub T. And I'm assuming everything is balanced. But we can also write the total real power in terms of the line voltage and the line current, can't we? We just scale that right-hand side by 3. We now have 3 divided by the square root of 3. That's the square root of 3, isn't it? So now we get this total real power formula as the square root of 3 V line I line cosine of theta sub phi. And now somebody might say, your total real power at that load is 168 kilowatts. And they don't break it out to you in per phase. They just say your total real power is 168 kilowatts. Now you know how to relate that to your power factor, your line voltage, and your line current from this formula. Is that clear? What about the reactive power? That's the same, isn't it? Except now we have to use the sine of the angle. But this is now Q sub phi is V sub phi, I sub phi sine of theta sub phi, or V line over the square root of 3, I line sine theta sub phi. Now you know how to get the reactive power. Once you have the angle of the impedance, the line voltage, and the line current, you can generate the reactive power, either per phase or total. This is now 3 of the per phase pieces, or that's now again this square root of 3 V line I line sine theta sub phi. And now you can see that three-phase power is like single-phase power, but now you have these square roots of 3 floating around occasionally, don't you? So it's not 3 times for the total unless you have the per phase piece, then it is 3 of those per phase pieces. If you're given line voltage, you go out and measure between transmission lines. You measure the current flowing. Now maybe you have one of those clamp-on meters that can sense the current flowing without disconnecting the circuit. You can measure the current, the line current. Now you can figure out if you know the power factor, and there's many different ways of finding the power factor, aren't there? From the impedance, you could find the real power and the apparent power and take that ratio, and that's the power factor. A lot of different ways of finding the power factor, and you can now talk about the total complex power. If you have all of your P's and Q's, you have that. Or you could say, well, that's really the square root of 3 V sub L line voltage, line current at an angle of theta sub phi. Where that angle of theta sub phi, you can then write in rectangular form to give you your total complex power, S sub t, is the square root of 3 times the line voltage times the line current cosine of theta sub phi plus j sine of theta sub phi, and there's your P and Q. Questions on that? Yes. So the question was a good question. We derived this formula for what configuration? The Y configuration. We're going to prove that that works for delta by just repeating this process. Okay? So yes, that formula, since it only depends on line voltage and line current, it'd be nice if it worked for both configurations, and that's why it works, because really you don't have to know what's going on behind the terminals. Behind the terminals might be a black box, and all you have access to are the terminals A, B, and C. You can now measure the line voltage. You can measure the line current. Now, as long as you know the power factor or the angle of the impedance, you can generate your total complex power. And you don't need to know, is that Y configured or delta configured? Let's see if we can show ourselves that. Here's our delta connected load. So thank you. I had that question planted. You're aware of plants, right? In the audience? I didn't really, did I? We didn't. Oh, here, thank you. We didn't work ahead of time for that question. But now let's look at this delta connected load and try to just get clear on these concepts in the other configuration. V sub AB, is that a line voltage or a phase voltage? How many think it's a line voltage? How many think it's a phase voltage? How many aren't thinking? If you're confused, it doesn't matter, right? It's the same. That's the voltage across one impedance, so that's the phase voltage. And in this configuration, it's also the line voltage. It's between terminal A and terminal B. So you were all correct if you wrote something down. For those of you that left it blank, that's a lesson to you. You probably want to answer, right? Because I can't give you points for nothing. I know I'd like to, but I can't justify that. So what did I say that was? Phase or line? Oh, it was both, wasn't it? What about the currents? I sub A, little a, big A. Is that a line current or a phase current? So now I'm interested in what this current is. That's going through the transmission line, isn't it? So it's a line current. This one is now a line current. And what is I sub capital A, capital B? That's the phase. That's going through a particular impedance, a phase impedance. And in this configuration, like we had said before, now we have to worry about distinguishing between the currents in a delta load. Now our line current is not the same as our phase current, but our line voltage and phase voltage are the same. Is that clear? Now we can walk through that same process that we did before. What's the power, real power per phase? Well, now you just have to go back and say, well, what was my phase voltage? That's the magnitude of VAB, wasn't it, in this case? And that's the same as my line voltage. Well, let's just do it one at a time. So P sub phi is now, let's just say it's V sub phi, which in this case was the magnitude of VAB for this configuration, right? So now V sub phi means maybe something different than what it did before. And then we have to take our phase current, and that was, in this case, I sub AB, wasn't it? And cosine of theta sub phi. Now, in terms of line variables, what do I replace these with? V sub phi, is that related to the line voltage? It's the same, isn't it? So now this one becomes just V sub L. But what is I sub phi? We haven't derived that yet, have we? I sub phi is I sub AB. But I sub AB is a phase current. Will show, I think, somewhere. I lost track of my script. Somebody stole my script. My teleprompter is not working. So I can't read anymore. And you know that I can't read if I take these off, right? Is the screen still blurry? Why did I say that? Last time the machine was dead, so that wasn't even recorded. Now it is, maybe, maybe not. Well, we're going to show that the phase current and the line current are related by also a square root of 3. But which would you expect to be bigger? I sub AB or I sub AA? In this configuration, if you did a KCL at terminal A, I sub AA is really being made up of 2 of the phase currents, isn't it? So you would think that IAA might be bigger in magnitude. And that's actually true. So that the line current, which is I sub AA, is I sub L over the square root of 3 cosine of theta sub phi. And now that square root of 3 factor comes because of the line current and phase current distinction in this configuration. But if you just knew the line current and the line voltage, you could compute, and the angle of the impedance, you could compute the per phase, not knowing what the configuration was. So that now the total real power is this square root of 3 V line I line cosine of theta sub phi. And now we can just complete this process. The reactive power again, it's VI, and those V's have to be phase voltages. The I has to be phase voltage if you're doing a per phase. Sine of the angle of the impedance, or that's also this V line I line over the square root of 3 sine of theta sub V. And our total then reactive power is this 3 times Q sub phi, which is the square root of 3 V line I line sine of theta sub phi. And if we want the total power, complex power, we just add together horizontal and vertical pieces. The total is the horizontal real part. The vertical is Q. If Q is positive, what kind of a load did we have? Inductive or capacitive? If Q is positive. Inductive, right? We're going up. That means it's inductive in our Q. And we can also then write this as this square root of 3 V line I line cosine of theta sub phi plus J sine of theta sub phi. Again, where this is now the angle of the impedance of your load, or this theta sub phi is now related to the phase voltage angle and the phase current angle. Now what we snuck in here was this relationship between line currents and phase currents in a delta connected load. I just sort of gave you that answer. But if you need to look at that, you can look in figure 1113, and let's just compute that for grins. Meaning our diagram now in very rough settings, I don't know why I drew my impedances so large, but let's say this is now our load impedances in a delta configuration. Let's say this is A, this is B, and this is C. Here is our line current, I sub AA. Then we have our A phase current, I sub AB. And then we have our other phase current that we need to keep track of. And that's coming from terminal C to terminal A. That's now I sub CA. And if you needed to draw it, you could draw I sub BC. We want to find a relationship between the phase currents, which are the double subscripted capitals in terms of the line currents, which have a lowercase and an uppercase variable subscript. We can do that by looking at, let's say, KCL at A. And there, KCL, it's our friend, isn't it? We just have to make sure that we do it properly, that we keep track of all the vector relationships, or this is now in phasor terms. It's not just magnitudes. We have to realize that we have I sub AA going in. We also have I sub CA going in, and that equals I sub AB leaving terminal A. Is that okay? That's KCL. Let's now solve that in terms of our line current I sub AA. I sub AA is now equal to I sub AB minus I sub CA. With our terminology, I'll do the hard part. Those are both A phase currents, aren't they? But are they the same current? No. Which one is which? Which one is the line current and which one is the phase current? The transmission line current is I sub AA, and I sub AB is going through one of your phases in your load, and that's the A phase by convention. And this is now the A phase current. Now, to continue, we need to make an assumption, or just commit to something. And what is that commitment that we have to select now? In order to continue, in order to relate the line current and the phase current, what do we have to assume? Yeah, we have to play in a circle, don't we? We have to figure out what circle are we moving around. We're either positive or negative, right? So it's the positive phase sequence or the negative phase sequence. We have to decide one or the other, and once we've done that, then we can continue. Let's be positive, okay? So that means we have the ABC sequence. If we have the ABC, or positive phase sequence, and let's just assume that the A phase voltage is our reference phasor, how would you express that? That's what we're wanting to be our reference. That's the A phase current, and we're going to use that as our reference phasor. Let's just pick an amplitude, right? We're assuming everything is balanced, and that's our phase current. Let's just call the amplitude I sub phi. It doesn't have a bar over it. That's just a number. And if that's our reference vector, let's make life easy and assume that's at 0 degrees. That's now our assumed reference phasor. If that's the case, what's I sub BC? Where'd that come from? That came from our positive circle, didn't it? So now we're walking around clockwise or the phasors are spinning counterclockwise bias, and we'll see ABC, ABC. That means the B phase is 120 degrees behind the A phase, and the C phase is 120 degrees behind the B phase, so it's minus 240, but that's equivalent to plus 120. Now we can come up with our relationship for our line currents in terms of our phase currents for the delta configuration. We just have to go back here and replace I sub AB with I sub phi at 0, I sub CA with I sub phi at 120 degrees, and take their algebraic sum, and keep track of the real and imaginary pieces of that vector combination. Meaning, we now have I sub AA is equal to I sub AB minus I sub CA. Now we have 120 degrees positive. Our sine piece is positive, our cosine piece is negative, but we're subtracting those. And so what do we end up with? We have the same kind of numbers floating around for our magnitudes. If we did this, it would be, we could say factor out the I sub phi, and I now have 1 minus cosine of 120 degrees plus j sine of 120 degrees. Doing all of that algebra ends up with the square root of 3 I sub phi. We now have a real part of 1.5 and an imaginary part of minus square root of 3 over 2. And that's going to give us a negative 30 degrees, isn't it? And now what do we have? Now we have our relationship between our, if we said that this was I sub AA, then this might be the, well, the magnitude of that is now the square root of 3 I sub phi. And this is actually I line, isn't it? And that's where our relationship between I sub phi and I sub line came from in the previous development. Questions on that? Now you know how to relate powers. You know how to distinguish between phase and line quantities or variables. You know all about power. And the right answer is this way, right? If we're bobbleheads in the back window of your vehicle, you guys probably all have bobbleheads, right, in your cars? I guess not. All right. Let me give you another quiz. We're just full of quizzes, aren't we? Well, I'm trying to get you ready for a week from today. All right? This is a word problem. If the line voltage in a balanced three-phase Y-connected load is 130 volts RMS at the load terminals, and the line current is 2 amps RMS, find the power factor of the load if the total three-phase inductive load consumes 120 watts. It's not a very big load, is it? That's a light bulb. You have a 100-watt light bulb. That's not a very big load, is it? I know you don't do it anymore, but if you had a hair dryer and you use that to dry your hair, that's like 1/10 of your hair dryer. So this is a pretty small load, isn't it? But it gives us something to play with. I have to wait because I have writer's cramp from writing that word problem down. But now do you see how you can really impress your roommate? You can just kind of lay that on the table or on their desk and say, this is what I'm working on. And then just see what happens, right? So you just sort of set something out in front of somebody and then you just kind of see what happens. Well, in this day and age, you probably have a camera so you can record what happens, right? All right. If the line voltage is a balanced three-phase Y-connected load, if it's 130 volts at the load terminals and the line current is 2 amps, find the power factor of the load if the total three-phase inductive load consumes 120 watts. Where do we start? Do we drop back 15 yards and punt? No, I'm trying to get you ready for next week. That's why we're training now, right? You don't want to stay up all night the night before and come in and try to take the exam. You want to start looking at some of those old exams now, tonight, while your roommate's struggling with this problem. You can go and look on D2L, right? Anybody have an answer? Okay, if I'm asking for the power factor, first off, how many pieces are involved in my answer? Now, that was a pretty vague question, wasn't it? I'm looking for a number and a description, right? And that description is one of two possibilities, and I've actually given it to myself here in this problem. Inductive load. So if you couldn't even solve anything numerically, you could get 2 points out of 100, right? For getting half of the answer. Yes? Hopefully you know that it's what kind of a power factor? Lagging, isn't it? It's lagging because of the inductive nature of your load. So you could write down PF equals blank lagging, just to get started. Got half the problem. Now you have to get the other half, all right? But what were we told? And what kind of power? You now need to start asking yourself, is that the total power? What kind of power? Is it complex? Is it apparent? Is it reactive? Is it real? It's the total real. And how do we've been labeling that capital P sub capital T, haven't we? So now we know that that is 120 watts. Do we have a formula for that relative to some of these other variables that are in the problem description? Yes, we've been deriving those all afternoon, haven't we? Good afternoon. Can't even remember what time of day it is. Oh, it has a PM here. Okay. Afternoon. Where were we? Oh, this is now square root of 3 V line I line cosine of theta sub phi. Yes? And then we didn't have to know what kind of connection we were dealing with. We didn't have to know if it was Y connected or delta connected, did we? And now we can start, oh, and we were asked for power factor, weren't we? Do we have everything else? We have everything else. This was an easy problem, wasn't it? So you could just really impress your roommate and say, it shouldn't have taken you more than 30 seconds. Right? This is now, the power factor is now P sub T over the square root of 3 V sub L I sub L. So we have 120 divided by the square root of 3. Our load, our voltage between the terminals of our load was 120 RMS. It's important that we've converted to RMS if it's not expressed in RMS. The current was 2, and did anybody compute that? What? Oh, man. I gave that to my roommate and went to bed, didn't I? Fell asleep. So that's now square root of 3, 130 times 2 for the denominator. So if you did something like that on the test, you'd get 4 out of 100. If you, yeah, that'd cost you 96 points. That 2 and 3 mistake. This is now pretty small, isn't it? Questions on that? Now you know how to start using these formulas. Let's look at some load transformations. We've been playing with transforming voltages and currents. Let's look at load transformations. And what section did I say this was in? Good. You guys remember better than I do. So this is 9-6 in your textbook. What we're wanting to do then is really just keep track of how we've labeled these configurations relative to each other. Let's say this is now Z1 between A, why am I using lowercase? I don't know. I'll just stick with it. Z1, Z2, Z3, or that's the delta configuration. We could have a Y and let's not assume to begin with that any of these Z's are the same. Z1 may be different than Z2, may be different from Z3, and we have to keep track of those. We want to be able to convert between either a delta to a Y or a Y to a delta, and that might be helpful if you had a Y delta configuration and you go, I want to solve this knowing my YY configuration, single phase equivalent. I want to now convert this into a Y configured load. What we're looking to do then is find expressions for the impedance between pairs of terminals in the two different configurations and set those equal to each other. Meaning, on the left-hand side, if I wanted to know what's the impedance seen between terminals A and B, I take my ohm meter and I connect it up to AB and I let C float. What's the impedance then seen if C is infinite? It's off in Never Never Land. It's not connected to anything. What's the impedance seen between terminals A and B? And I'm going to assume that we're now playing with an unbalanced set of loads. If I look at that and I say I need to find the equivalent impedance, I have Z1 in parallel with the series Z2, Z3. Yes? In the left-hand side configuration. So that now I have Z sub 1 times Z sub 2 plus Z sub 3 all over their sum. That's the delta configuration impedance between terminals A and B. What if I did the same thing with my Y connection and I said, what's the impedance between A and B? On the right-hand side. And again, C is floating, hanging. Does that make sense? It's just the sum of impedance A and B, between A and B. Z sub C is, you could just snip that off. It doesn't matter what that is, because it's floating. Oh. Wow. It's not a good sign, is it? Got to going too fast. So let me just talk my way through this. What am I going to do? I'm going to find that same relationship between the different pairs of terminals, BC, CA. And I will get the same kinds of structures on the left and right of both of those. Now I just have to do some algebra. And one of the algebra steps that you can do is you can actually take this first equation, subtract your next equation, and add the third equation, and you'll end up with a relationship between all of these. And if it would quit spinning, is that a positive phase sequence or a negative phase sequence that it's spinning on? It's got to be negative, right? It's going to be broken if it doesn't quit. Now you're going to see this guy get angry, huh? Whew, that's ugly. You don't want to see that. It'll follow me around. Look at that. Oh, I can just play. All right. Wow. We've still got plenty of time, don't we? So let me see if I can do that. What? Oh, that's right. My time has stopped. No, it hasn't. So it's still hanging in there a little bit. It's just having trouble. So this time I'm somewhat prepared. Well, you can see the configuration. Oh, but I'm going to have to turn one off, aren't I? Boy. I feel like I am in the chemistry building and I'm ready to do an experiment. I'll pull out some beakers, have an explosion. Is everybody ready? Ooh. Ooh, if I start choking, you know why. What do I want to do? Let me go to a blank slate. And now I have, is it in focus? Ugh. Let's do BC. You have it in your notes, right? So let's look at the combination between B and C. That was now Z2 in parallel with Z1 and Z sub 3. Good thing I had a manicure before. Never mind. I hope that's right. And then that was equal, that's between B and C, so that, to be consistent with what we had before, is Z sub B plus Z sub C. And then we have our CA configuration. And the CA configuration now says that we have Z sub 3 in parallel with Z sub 1 and Z sub 2. Why are they equal? We are forcing them to be equal so that we can convert between the two different kinds of representations. So we are assuming that these appear to be the same impedances, whether it's in the delta configuration or the Y configuration, and we're asking under what relationships between the two will that be true? And that's why we're able to set those equal to each other. This one now is Z sub A plus Z sub C. And the first one that we had, which is still spinning, and you're going to have to maybe keep track of the time. I guess it's still sort of keeping track of the time. This was now our Z1, Z2 plus Z3 over Z1 plus Z2 plus Z sub 3, and that was equal to Z sub A plus Z sub B, and that was our A, B configuration. What I had suggested that you could do to try to solve one for the other was to take the AB row equality, subtract the BC line, and add the CA line. Do that on the right-hand side. We take ZA plus ZB minus ZB minus ZC, so the ZBs are gone, plus ZA-ZC. Now the ZCs are gone, right? And we're left with two ZAs on the right-hand side. Meaning I took this equation, or this line, the blue line, subtracted the second line. So if I said there's 1, here's 2, and here's 3, I took 1 minus 2 plus 3. And if I do that on the left-hand side, it's a little bit more tedious with the algebra, but we get 2 Z1, Z3 over the same denominator. And this now gives me a relationship between my A phase in the Y connected load in terms of delta impedances. And I could do the same thing to find Z sub B and Z sub C. Then I do algebra and I find Z1, Z2 in terms of ZA, ZB, and ZC, and that's done in section 9.6 of the textbook. And that allows you now to convert between the two. If everything was equal, if all my numerical subscripts were z deltas, then I would have z delta over 3z delta is equal to zy. And I can cancel one of those, and now I can see that my zy is 1/3 of my z delta. This is if everything was balanced. And we'll pick up at that point on Tuesday. Sorry for the crash.